Okay, in this video we're going to talk about the chemical shift or the position of the peaks in an NMR spectrum. All right, so we've already talked about how many signals there should be. Now we want to talk about where in the spectrum, where on the x-axis these signals are going to be, and we call this the chemical shift. So one thing that we often do when we take NMR spectra is we actually add another compound to our sample. And the specific compound that we add is tetramethylsilane, or TMS, and TMS is used as an internal standard. So the frequency of the radio waves that the protons in TMS absorb is lower than most other organic compounds. And so what we usually do is set the TMS signal to be 0, and then we measure the frequencies of the radio waves that the other protons absorb relative to the TMS. And so this shift relative to the TMS is dimensionless because the hertz cancel out, but very often you'll see the units they put on the NMR spectra are in ppm, or parts per million. And so most of our signals are going to appear between 0 and 10 ppm. Now, how far the signals are shifted in the NMR spectrum is determined by the electronic environment around the protons. Basically, the more electron density there is around the protons, the further to the right they will be in the spectrum. And we say that those protons are shielded by the large density of electrons that they have around them. And when we're talking about NMR spectra, peaks that appear on the left-hand side are often referred to as being downfield, and peaks that appear on the right-hand side of the spectrum are referred to as upfield. And you can see we have the peak from our TMS internal standard here down at 0. So these peaks that appear upfield tend to have higher electron density around the protons, and we say they're shielded. These peaks down here represent protons that have less electron density around them, and we say they are de-shielded, and they are downfield in the spectrum. All right, so just to give us a starting point, when we have CH3s or CH2s or CHs, they have somewhat different chemical shifts, and then depending on the environment, things can be shifted further downfield. And so one of the big things that plays a role in de-shielding these protons are inductive effects. And inductive effects are when we have an electronegative atom that pulls electrons toward itself, right? That means it's pulling it away from the protons, and it's de-shielding them. And so we can see the effect here when we add a halogen to this methane. Right? When we just have methane, its chemical shift is 1 ppm, and so it's fairly far upfield. Right? As we add more electronegative halogen atoms, we can see that the chemical shift increases, right? So fluorine shifts the peak further downfield than the iodine, right? And the more of those electronegative atoms that we put on, the greater the effect is. Now, distance also plays a role. The closer the protons are to the electronegative atom, the greater the shift will be. So we get a shift of 3.3 for the hydrogens right next to the chlorine, right? And then that the amount that the protons are de-shielded decreases, and so does the chemical shift. All right, so oxygens are also electronegative. They're going to shift our signals to the left in the spectrum. They're going to shift them downfield. And you don't have to have these numbers memorized, but I just wanted to show this slide to show that different oxygens are different, right? And so when we have an alcohol or the oxygen here from an ester, right, that has a fairly large effect. We also have the effect of being next to a carbonyl group, which shifts it, about 1 downfield. Now, there are some examples in the book where you actually have to calculate the chemical shifts. We're not going to do a whole lot of that in sort of quizzes and exams, but I think it's good practice to do at least a couple of those so you can see what the different effects of these substituents are and how the chemical shifts are going to be different for protons in different parts of the molecule, depending on how close they are to these electronegative atoms. So another thing that can de-shield electrons and have these peaks appear downfield is when we have the presence of a benzene ring. So we don't need to worry too much about the details, But when the delocalized electrons in the benzene ring are put in a magnetic field, it results in deshielding of the protons that are attached to the benzene ring, and it has a similar effect on protons that are adjacent to the benzene ring. And so this signal down here, just above 7 parts per million, is characteristic of these aromatic protons on a benzene ring. And so when you see a whole bunch of peaks down around 7, that's a good indication that we have a benzene ring. And what we're seeing is the aromatic protons. And then you can also see this peak is due to the CH2 group. This peak is due to the CH3 group, and normally these CH2 and CH3 groups would have chemical shifts, sort of in this region, right? But because the CH2 group is right next to the benzene ring, right, it gets shifted downfield somewhat. Now the CH3 group is further away, right, and so the effect on it is less significant, right? And you don't have to have all these different chemical shifts memorized. You'll be provided with this table when we're in lab and when we're doing quizzes and exams, and so this is a helpful reference when we're trying to assign peaks.